Okay, so I think many of you have joined, around 25 have joined. So this is the second lecture that we are going through, and I was discussing that how you should be preparing your strategy for the GATE exam. So if you think that GATE 2023 you can clear, or even if you think you cannot clear, you are anyways giving GATE, this 3-4 months of preparation you can focus mainly on the previous year papers, okay, maybe 8 to 10 years previous year paper for major subjects. So cover the major subjects first and then go to the minor subjects, okay. So today we will be taking some questions which I will tell you that which questions to actually take and which questions to leave during GATE exam. That is also very important. What happens is that during GATE exam we come across some questions which are actually not possible to solve at that particular time. It will take much time, it is very tedious, and there is high chance that you will end up with wrong answer. So those questions you should not touch at all, okay. You should always start with easy questions, whatever you can solve, and like that you should proceed, okay. One of you, I think Chandrasekhar, had sent me 3 questions he had doubts in. So I will take those. So before that, I had told you that we will start with MOSFETs today. So but I am not starting with MOSFET today, I am starting with electronic devices. MOSFETs will do in next week. So what I have decided is that today we will start with the semiconductor theory, some basic things I will tell you. Then next week again I will take MOSFETs. Then after that I will again take electronic devices, like today's thing, okay. So what will happen, there will be a 2-week gap between this topic, right. So in this 2-week gap you prepare this topic. So today whatever your position is regarding to this topic, after 2 weeks this position should improve. That is what I think. So I hope that will be fine with you. The thing is that if you search any topic in like Google or YouTube, you will find lot of lectures regarding to those topics, right. So if I also just lecture you on the topic, or I also show you a slide and just lecture you, I don't think that is going to be very much beneficial. So I wanted it to be an interactive doubt session kind of thing, where I can actually tell you the tips or tricks of how things should be taken care of, okay. So without wasting much time I will start. So the thing is, for electronic devices I was searching for NPTEL lectures, okay, and I was searching for this NPTEL lecture and I could find only one lecture with electronic devices, and that lecture actually covered whatever main topics that come in GATE. So first I will share my screen and show you what are the topics that I had listed, and then I will show you that lecture. So whoever is preparing with a strategy of 1 year, or is in the 2nd, 3rd semester of college and deciding to prepare for GATE and they have 2-3 years on hand, you can go with this method of preparation. For those who are really like who will just give 23 and they won't give 24, 25 GATE exam, they are only giving 23, for you watching this lecture and preparing will be a bit too much because you don't have much time. So for them also I will tell how you can like come up with the solutions, how to solve your issue. Otherwise, so let me start. I will just share my screen first. You are able to understand what I am saying, right? I can speak in Hindi as well, so if you want I can mix it up, but I think there are South Indians also who might not be comfortable, so whatever works for you works with me. English, proper English is fine, right? Completely in English, okay. Yeah, of course. Right.
Ma'am, I have a doubt. Should I ask?
We will take doubts and final.
No, ma'am. Doubt is not related to
Okay,
any
okay, yeah.
questions.
Okay, you can ask.
मैम मुझे ये पूछना था मैम, जो NPTEL लेक्चर जो इस साइट पे है वो इनफ है अगर हम वो लेक्चर को कर लें जो अभी दिया है?
Okay. So what happens? So what Mamta is asking is, Mamta, you can mute yourself. Okay. So what Mamta is asking is that whether the NPTEL lectures are completely enough for GATE preparation. Okay. So I had mentioned you in the last class as well. NPTEL lectures are very much detailed. So they are more than enough for your GATE preparation. They are enough for any other exam as well that you are going to take or you are planning to take. right? Normally who prepare for GATE also give civil services as well as engineering services, if I am not wrong, right? So they are more than enough for both the preparations. Okay, in civil services, of course, the optional is electrical, it is not electronics, so you have to prepare electrical subjects for that. So let me keep that aside. I am not here to talk about IES or IAS. I am here to talk about GATE. So they are more than enough for GATE. So the problem with NPTEL lecture is you will have to choose what to watch and what not to watch. So if you have 1 year in hand or you have 2 years in hand for your preparation, then you should watch everything first to last, okay, because otherwise the continuity will break. I will show you how that happens. Or else you can choose what to watch and reject what not to watch. Today I will show you that. I have selected one course and I will show you how to go about it, okay. So I hope this doubt will be getting cleared. NPTEL lectures are more than enough for GATE preparation, but remember, they are not going to show you GATE questions and solve them for you. They are not going to show you that okay, this is asked in GATE and this is not asked in GATE. They won't utter the word GATE because it is not meant for GATE, right? Okay. Ma'am, do we have access to recorded lectures? This recorded lecture that I am speaking right now. So this lecture I will upload a bit late. Till now we have not got any kind of communication from NPTEL side. So I will upload this in my YouTube channel, but I won't do it just after the class, okay. Maybe after 1 week or 2 weeks I will upload. Otherwise what will happen is you guys won't come in the live lecture and you will sit watching that, which does not make sense, because I want this lecture to be completely interacting so that your problems are solved, okay. Otherwise you can go to YouTube also and watch, but there they might be having 1000 subscribers, 10,000, 20,000 subscribers. They might not answer to you. Here you are 30-40 people, I can answer to you, okay. So let me start without wasting time. Okay, so as I had said, this Streetman Banerjee book, right? Streetman Banerjee book, chapter 2, 3, 4, these are all 5, these are all related to your initial semiconductor theory that is asked in EDC, okay. So what is that? Chapter you will see 2, 3, 4, all these are related to semiconductor theory, okay. Now as I saw in the last 2 years paper, 2-3 years paper, they are asking most of the question from excess careers in semiconductors now, this topic, okay. This excess careers is what is being asked now mostly, okay. So earlier it was more from the quasi Fermi levels. I am not saying it won't be asked now. Quasi Fermi levels can be a hot topic now also, but it might be limited to 1 mark question, okay. But excess careers I am seeing generation recombination question, they are asking for 2 marks as well, okay. Both 1 mark 2 mark questions are there. Simple questions are also there, very tough question is also there. We will solve one, we will see. There is a one with 2022 that they asked, okay. So in the chapter 4 of Streetman Banerjee, you will get direct and indirect bandgap semiconductor, okay. This topic you will get. From this topic you can get a 1 mark theory type of question you can get. From this topic you can get a multiple correct question, direct and indirect bandgap semiconductor, okay. So these topics are very good for this multiple select questions, I think they say, right, MSQ something, right. So this can come, multiple answers correction, those kind of questions can come. Excess careers, generation and recombination of career, okay. So this is basically upon illumination of a semiconductor, excess careers are generated and then they recombine also. So there is a graph related to that and there is some exponential expression related to that, and they keep on asking questions from there, okay. Because wherever there is a graph involved and there is an exponent involved, questions can form, numerical questions can form, theory questions can form. So that is what they are asking, and Chandrasekhar has also sent me one question related to the same thing, so we will take that. Next is quasi Fermi levels, that is whenever there is this excess career kind of thing, your Fermi levels will be disturbed. Fermi levels are nothing but the energy level of your electrons or holes or the carriers. So they will get disturbed, and the questions from there come, that also we will see. Current density, after that comes current density. Okay, so if there is this motion of charge carriers, there will be obviously a current. So from current you find the current density, and this has always been a hot topic for 1 mark question answer and 2 marks also. A lot of questions you will see from drift and diffusion current density. Okay, but last 2 years I am not seeing that. Mostly questions are from excess carriers, and that is because now the GATE exam has become very competitive, right? So with so many students coming up, and students are very much like they can easily solve these questions now. So therefore they are upping their game, they are upping the questions. Okay, so therefore they are now touching those topics that were not that much touched earlier, and they are framing very good questions out of it. Continuity equation is one such topic which was earlier also was there, and now it will be more. Okay, I think continuity equation will be more now. It's a good topic. So for lecture you can see Professor S. Karmalkar, IIT Madras lecture, very old lectures, but I saw he has covered everything, and I will show you from there what to study, what not to study. Okay, so you guys can take a snapshot of this first, take a photo of this. Some of you were asking for notes, so these are not proper notes. Okay, so I cannot give you these notes like that, but I will upload them in my website. I will again put the website link here. In my website I will make a section of GATE, and in that I will lecture wise I will just put whatever I am teaching you here. Okay, so but please don't take them as hard and fast lecture note kind of thing. This is just for interaction with you. So have you taken a screenshot, everybody? Because this you will have to refer. I'll stop sharing my screen and I'll show you something else. So by that time you will have to refer this. So please take a photo of this, or else just quickly write this thing, lecture 9, 10, 11, 12, 13, 14, 15, 16, 17. So lecture 9 to 16, and we will see what they are. Okay, so I am stopping my share of screen, and I am sharing the other screen now. Can you see my screen now? Anyone? Unmute yourself and tell me.
Yes.
Okay, okay. So if you go to the NPTEL website, it is like this. In NPTEL website you enter courses. Okay, NPTEL courses, and in courses if you put devices as the keyword, or you just search it. Okay, any way you want to search, you can search it. So solid state devices. Okay, Electronics and Communication Engineering, Professor S. Karmalkar, IIT Madras. If you click here, okay, I think you will find this in the videos as well in YouTube and all. You will be able to find the videos. Okay, now here if you go to syllabus, if you click on syllabus, the syllabus will come out, and there is download section. In downloads, if you see books, okay, if you click on books, in English there is a download available, and I don't know what is there in transcripts. Okay, so in transcripts you will the thing is available in related to each and every topic, like every lecture the corresponding transcript is there, but the corresponding transcript is there, but if you go to the book, okay, the book is basically nothing but the entire transcript together. So if you open the book, this opens, and this is nothing but a 1000-page transcript of his lecture. Okay, so from the transcript you can directly see where in which lecture he has taught what, right, and then you can go back to the lecture and listen to the lecture. Now here he has also given the syllabus. So if you see the syllabus, evolution and uniqueness of semiconductor technology, introduction, leave these two, we don't need that. Just check what he has shown, read it, just see. So if you see it here, you can see he is just showing the semiconductor devices. We can leave this, okay. Basics he has touched. If you don't do this, anyways, later on you can do this in the chapter, somewhere he will again tell you. Some things I think here he has shown intrinsic, semiconductor, metal, this difference. You can just read it up and understand. You need not listen to the entire lecture for this thing, okay. Then properties of semiconductors, quickly you can go over it. So this is what referred time is, okay. The timing he has given. So from here you can directly jump to the topic and check whatever he has taught here. Drift diffusion, this is a bit important, so you can go over it, okay. So after this he has given some kind of basics about his course content, fine. So you see now the lecture 2 has started. Now in the lecture 2 again he has discussed some basics, processing kind of thing, and then he goes with that. So you can leave this kind of things, okay, and then you go to the part where your actual thing starts, right. So now you see here, if you compare with your GATE syllabus, Carrier transport, random motion, drift diffusion, all is there in GATE. Excess carrier, injection level, lifetime, direct and indirect, this is what I was talking about. This is a very important topic now, this is coming, okay. Now here procedure for analyzing semiconductor devices, basic equations and approximations. This topic directly is not mentioned in GATE, but if you look into its syllabus, this is a very important thing. All the formulas he has taught you here, okay. So these 3 parts are quite important. Now after that the p-n junction starts, and whatever is important in p-n junction, BJT, everything comes in. So okay, so from his lecture, this lecture you can completely follow for electronic devices, okay. Now if you go in the transcripts, as I had asked you to take a photograph, right. So if you see lecture 9, 10 and 11 are charge carriers, Fermi levels, all these things have been discussed. So let me try to see where lecture 9, 10 is there. Which lecture is this? I think it is, okay, this is 5, equilibrium and carrier concentration, okay. So I am not asking you to completely skip this. If you have ample amount of time in your hand, you should from first to last you should watch it, or otherwise you can directly go to the particular chapters that I am mentioning and directly take things from there, okay. So this was 5. So around 9, 10, 11 here he has started discussing the energy levels, okay. This is important for us, questions come. 7, chapter 7 is energy levels, okay. So here he has discussed about your Fermi level graphs and everything. So this is important, okay. Chapter, this is I think chapter 7 or 8. This equation is Fermi direct function. This is what this used to come a lot in GATE. Recently I haven't seen the thing coming, but that means it can again come, because it used to come earlier, in between they have stopped, so again they can give, okay. This is also a very important graph. This lecture you should completely go. Lecture number 8, equilibrium carrier concentration, still continues. This is important lecture, okay. The formulas that are given are important. Directly with GATE what happens is, this NIPI, this entire expression formula will not come. What they will give is, they will frame the question in such a way that any one relation you will have to use. Either this relation will come into use, or this relation, like the proportional relation, will come into use, not the entire formula. I hope you are clear. If you are unable to follow me at some point, you can stop me and ask, because I am a fast speaker, I know. So if you don't understand, please stop me and ask, okay. So these formulas are important, okay. We will discuss this today. These formulas are important. So these formulas he has covered, and after that I think Fermi direct is covered till lecture 8. Now from 9, 10, 11 he has started describing these formulas, these important formulas he has started describing. Okay, so 9, 10, 11 goes with that. Then comes, okay, now 12, 13, 14 he has discussed current density and mobility in too much detail. Okay, current density and mobility in too much detail in 12, 13, 14. That much detail we don't want, but again if you have time you should go over to everything. If you don't have time, you just see what all the conclusions he is drawing, what all the conclusions he is coming to. Like for example, this diffusion current expression, okay, whole diffusion current expression, okay, this is what comes in gate. So this expression is his conclusion, but where it holds, so it is written may hold for minority carriers under low level condition. So these are the things now you want to know. Now gate pattern is changing a bit, they are involving too much trick in the question. So they will make the conditions something like that, that this equation might not hold. Okay, so those things you have to understand. So for that we have to look into the lectures. Okay, so yeah, so 12, 13, 14 too much in detail. If you can, you go through it, otherwise you can quickly skip over. But these are this steady state equation. Always remember, whatever equations result in the steady state of the semiconductor, those are important. We will see that in questions they give under steady state condition find this. So those things are important. Okay. Now questions have started coming from these kind of topics. These topics they have started. Whatever looks complicated, now they have started. So you see he has written some cos h, sin h function. These things are not important. He has written it to show you how this graph comes, why this kind of graph, why this kind of curve comes. Okay, nobody will tell you these things. Only in NPTEL lectures you will find this amount of clarity. Okay, so this is very good thing to understand, because everyone will tell you that okay, it is related to e to the power minus x. Why nobody tells you? So that you can understand from here. Okay, so but for gate point of view, that much detail is not needed. You only need the formulas, right? But according to me, you should know where to use the formula properly. For that you have to listen and understand the lecture. So all these lectures are related to excess carrier concentration. Okay, now procedure for device analysis, this is also very important. 15, 16, 17 I think, 18 was also there. Okay, here he has I think yeah, 18 I think it is not that much required. Till 17 you need for gate, mainly till 17 they have asked in gate exams. Okay, and I think continuity equation is this somewhere, no, I think continuity is done till lecture 17. Okay, so till 17 you can go over this, and then again when PN junction starts, you can start with the PN junction. Okay, when PN junction starts, you can start with the PN junction, and likewise whatever strategy I told you right now for this semiconductor device theory, you can also apply it to the MOSFETs or BJT or PN junctions as well. Am I clear till this point? Any doubts now? Any doubts on this? So Mamta, is it clear to you now what you had asked, that whether it is sufficient or not, or how to study from NPTEL lectures, what to study and what not to study?
Yes, ma'am.
So the problem is that you will have to spend some time to figure this out. Okay, because there is no one spoon feeding you, right? No one has done this analysis for you and just telling you that okay, you read this, you don't read this, right? That is what they do mostly in these preparation centers that are there. They do that only. So that work you don't have to do. But what happens is that they directly spoon feed you. Here you will have to do a bit of that work. So you can go through the NPTEL lectures, you can go through the previous year papers, and you can decide that okay, this is the topic they are asking, so I can read this and I can leave this. That you can do. Okay, from there also in YouTube, if you search the similar topics, In YouTube they have videos for this GATE preparation. There are many teachers across the country or who actually help prepare the videos, help prepare for GATE exam. So those videos I have seen are very much to the point to GATE, but I don't know how beneficial they are because I have never completely thoroughly studied from there. Okay, so those videos also you can take help to understand which topic to do and which topic to not do. Okay, so from
Okay, ma'am.
okay, so I hope everyone is clear on this. Anyone else wants to say something? Be very free. Any doubt? So today I have given you this EDC thing. Okay, if it is not like coming in between with your preparation strategy, you can start the EDC and then again after 2 weeks we can resume with this access career topic. Okay, okay. So let me now again share my other screen and I will tell you quickly the EDC topics that are mostly used. Okay. Someone has asked me to solve continuity equation problem. Okay, if you can, I have taken a lot of problems today, but direct continuity equation problems you can search and send it to me. Okay, as the doubt you can send. I think Jyoti has asked me, so you can send it to me over my email, and then we will take it over. Okay. Okay. So next is the formulas that are majorly there. Expression from where numericals are mostly asked. First is the Fermi Dirac function. I will upload this one if you guys want. Okay, but don't take it as a formula chit, something like that. Don't use it like that. This is just to tell you the topics. Okay. So Fermi Dirac function is nothing but a probability of charge carriers occupying a particular level. Okay, so this is where the questions are asked from. Then what is the concentration of electrons in conduction band, concentration of holes in conduction band. Okay, these formulas are there, many questions have been asked from there. Okay, this is important. Mass action law is important, Ni square is equals to Np. Okay, from here you actually arrive at this formula also. These formulas are all related, and I will advise you that you should do these derivations. Okay, so what I used to do was I used to do a lot of derivations, and because of that till date I remember the formulas. I never used to mug up the formulas, I used to do the derivation. So what I will do is I will start from mass action law and I will start from Dirac function, and then I will arrive at this equation, I arrive at this equation, like that I used to do, and from here I will arrive at some other equations that are needed. Okay, so like that what happens is even during exam you don't remember exactly the formula, you can derive it and cross check it, and very quickly you can do it. If you are in practice you can do it very quickly. Okay, so for example this,
Ma'am,
yeah,
I have one doubt. Ma'am, like, can you explain basic concepts like what is access carrier, what is
no,
Foster
see,
Fermi
that is
level?
what I am saying, that you will get a lot of uh, videos on explanation of how access carriers are generated, what is quasi Fermi level and all those things. Lot of videos are there. Just now the NPTEL lecture I showed you, that also has that. So 1 hour lecture per week is not enough to explain these things. If I do that, then it's gone. Okay, nothing, we won't be able to finish anything. So those you will have to work and you will have to find out from yourself, from your side. Okay, if I keep on telling that, I don't know how many hour lectures I will need to finish up one topic. So that you can get from the NPTEL site or from YouTube videos. Is it clear? So I know you guys might want that I teach you from basic and one-on-one we teach and I give you questions to solve. I know you, that would be ideal, right? But I am taking only one class for 1 hour every week. That is too less. Okay, is that fine? So directly we will be dealing with doubts and questions. You guys, so Mamta, I think you can start with EDC. I have given you the lecture. Start with that lecture. Okay, listen to the lecture again and again if you don't understand. The professor has completely explained these things, and of course I am nowhere near him in explanation of these things. Okay, they are brilliant researchers and educators, so study from them. I think that will be the best thing to do. You will understand.
Yes.
You will understand each and every concept. Okay, so for example, if you see this thing, Ni square is equals to A naught T cube, right? So normally the question directly does not come from here. The question will be framed in such a way that you will be using this relation. Ni square is directly proportional to T cube. This is the relation which is mostly exploited. Okay, what they will do? They will say Ni at T equals to 300 Kelvin is something. They will give, suppose X. What is Ni at say 270 Kelvin? So this is the kind of question they frame. So what you have to do, you will have to just take the ratio and get the answer, right? So these kind of questions are framed. Okay, these next two formulas, if you see, they match the above two formulas. I am marking in green. This one and this one is similar, right? So this one comes from the other. One is the generalized formula of a Fermi level, and here the Fermi level is replaced with the intrinsic Fermi level. So what are these terms? Again, you have to go through proper lectures, you have to go through to understand this. Okay, so to those who have just now joined, I am going over the EDC, whatever expressions are mostly used. Okay, and I will make the recordings available so that from first to last you guys can see what is going on. Okay, charge neutrality equation, then comes the mobility of charge carriers. This is also important. This is the expression of drift velocity. Mu is mobility. Mobility's dependence on temperature is also important. There was one question, one MSQ question that was asked related to this. Effect of scattering on mobility. Then the conductivity formulas. Every time questions have been asking. Okay. Then the Fermi level in intrinsic semiconductor and extrinsic semiconductor. Okay. These are basically derived from the formulas that we saw above. Okay. Now shift in position of Fermi level. This is also important. How much is the shift, they ask. So direct formulas are there, but how we arrive at the formulas is what you should study. Okay. So these are one set of expressions. Let's go to the second set. Excess carriers in semiconductors. What happens is, there is a semiconductor, okay, normal semiconductor, any type, P type or N type. Okay. What happens is, if light falls on that semiconductor, electron hole pairs are generated. Okay, and always electron and hole will be generated in pair. Why? Because they are combined, right? They are combined, and when light falls, they got excited and they get generated. Now when they get generated, there is an increase in the number of electrons and there is an increase in the number of holes. So delta N is the increase, delta P is the increase. So delta P for holes, delta N for electrons. Okay. So what is the total number of electrons and holes after the steady state is reached? This is at steady state. What is the total number? This is the total number. N naught P naught was the earlier number, right? Then we know in the N type equation, there is this equation is there in N type. This is for P type. Okay. So in N type, what will happen? Donor will be more. So if donor is more, then P is the minority, holes is the minority in N type. Okay. Then in P type, Na is more, acceptor is more, and N is minority, right? Then you will study low level injection and high level injection. Okay. Injection, low level injection, high level injection. Mainly questions are coming from low level injection now. Okay. Low level injection is important. Excess carriers are less than 1/10 of the majority carriers, and in high level, excess carriers that are generated, the excess carriers, delta N, delta P, they are greater than 10 times the majority. That is high level. Okay. Now, if the electron hole pairs are generated, after some time they recombine also. So, there is one generation rate and there is one recombination rate. Okay. So, G is the generation rate, R is the recombination rate. Now, net generation is generation at equilibrium, whatever was generating at equilibrium added to the excess carriers that are generated. Then similarly for recombination, recombination at equilibrium and excess carriers that are recombined. Okay. So, this is a graph which is important. This is also there in the your thing the ADC NPTEL lecture, this is there. Okay. So, suppose here I have switched on the light and here I have switched off the light. During this time the light was on, it was getting illuminated. So, what is happening? This is the profile of the current, the next one I is the profile of current, and you can see earlier when there was no light, G and R will be 0, right? G and R will be 0. Then after that what happened? Carriers have started generating, therefore generation is greater than recombination, right? Now after some time generation becomes equal to recombination. After that recombination is greater than generation, because now there is no light. Here if you see in this part there is no light, that means no more generation. Now carriers will recombine. You got my point. So, this is the graph I am telling you in very much short. In details you can study this. If you see this one, this graph here, this is what is given by d delta by delta dt G dash minus R dash, and this graph here, this is given by d delta by dt minus R dash. Okay. Now, this is under low level, this is what the equation is. Tau is the lifetime of the carrier. So, when the carrier generated and when the carrier got recombined, between that what is the time? So, that is given by tau, and this is the equation we arrive at. This is important equation, delta n and delta p. Okay. Then will come diffusion current density, drift current density concept. Then Einstein's relation is also important, B is equals to mu Vt, where Vt is the thermal voltage. So, if it is for holes, dP equals to mu p Vt, and for electrons dN equals to mu n Vt. It might happen that you are unable to understand anything. Okay. Right now you are unable to understand anything, and that is fine. If you do not know these topics, you will not understand. But when I share this document, you will find the like you are saying that you do not know what you should study and what you should leave. So, what is there in the document is something you should definitely study. That is why I am showing this thing. Okay. Now, continuity equation is this one. Okay. Diffusion length is given by this. This is an important relation. We will use this in a question, we will see. Okay. Now, the next set of formulas, built-in potential, okay, contact potential or built-in potential. So, when you make a PN junction diode, when you bring together a p-type semiconductor and an n-type semiconductor and electrically join it, okay, it is not that you are mechanically just putting them together, you are electrically joining it. When you do that, there is a potential, there is a depletion width that comes. I think some of you might remember it from your college days. There is a depletion width forms, and here there is a potential forms, and this potential is called contact or built-in potential. Okay. In the chapter junction of Streetman Banerjee, you will get this. Okay. And you will also get it in the NPTEL lecture. So, this is a very important formula, this one. Then maximum electric field, how to find, there is a derivation that you do and you arrive at these equations. Okay. And then width is also this was asked in 2021 or 2022, I think, a question from here, width of the depletion region. Okay. And then width in the N side and width in the P side, because if this is the semiconductor P and N and the depletion width is formed, then this is the width at WP and WN, right. There is a width at P side and width at N side, and the total depletion width is given by WP plus WN. Okay. And the effective width of P side is what? It will be the earlier width minus WP. WP is the depletion width. So, mark the wordings, okay, mark the language. So these were some set of formulas. I hope this is fine. So these 3 pages I did only till PN junction. After that I think there can be more in PN junction, then diodes are there and things like that. One more thing is, I had mentioned you to go through SHORM series, right? So please, I was seeing one of the books and it's really good. EDC SHORM series is not there, but you will find it for solving numericals of analog circuits. The name is Electronic Devices and Circuits. The book name is Electronic Devices and Circuits, but the questions are mainly from this. And how to find SHORM's books? You can go to the website directly. Just Google SHORM series like that and it will take you to the website, and in the website you can search whatever book is there. Okay. So I hope till here it is clear. Any questions? So if you did not understand whatever formulas I showed you, it's okay, that is perfectly fine and understood. But I only want you to give an impression of what to study. If that is clear, then it is fine. Yeah, I will upload these notes in my website. I will put the link of my website by the end of the class. Okay, and you go to that web link and take the notes. Just download from there. Okay. Basically, I'll put it in my drive and put the link there, and then from there you can download it. So these notes are just for understanding what to study. Don't take it as a short note or something. Please, I am requesting you. Okay. Okay. So now there were some doubts, but before I go to the doubt, I will go to one question which was asked in 2022, and from there we will arrive at whatever equations I am showing. So basically I will be in the NPTEL portal, they will be uploading the gate solution videos also, and some of the videos I am also doing, especially for EDC and analog. Once that is uploaded, there also you can directly go and check out. Okay. So let me first show you this question. So consider a long rectangular bar of direct band gap p-type semiconductor. So it is a p-type semiconductor. Equilibrium hole density p value is given. Intrinsic carrier concentration Ni is given. Electron and hole diffusion length Lp and Ln are given. Okay. So what is given is here, I have written it in the side. Now left side of the bar is uniformly illuminated. Always mark this word. In gate paper, uniform illumination will always there. Non-uniform illumination is not there. Okay. Uniform illumination is there. At x equals to 0, uniform illumination is there. Excess electron hole pairs are generated only at x equals to 0. Now the steady state electron density at x equals to 0 is 10 to the power 40. So how do we mark it? I have written it here, side, NP0, right? You can see. So N means electron and P means the p-type semiconductor. So electrons in the p-type semiconductor at x equals to 0 is 10 to the power 40. Okay. Now under these conditions, ignoring electric field, what is the value at x equals to 2 micron? Okay, I have written here NP0, but in many cases you will see this NP0 or PN0, this 0 actually marks equilibrium point. Okay, it is not the distance. Okay. So what happens is, this follows a relation. The minority carriers, whenever there is an illumination, the minority carriers will start getting more excited. Okay. So in p-type semiconductor, what is minority? Electron is minority. So it started getting very excited. So when it started getting very excited, after that it follows this kind of a graph that I have shown. This is a graph of NPX, this is NP0, you see I have marked, and N0 is the initial concentration. It was a low concentration, and then what happened at x equals to 0, it was illuminated, so it actually jumped at very high value, and then after that as the distance increased, it actually was low. You understood? The graph is like that. So now what they have asked you to find out? They have asked you to find out the value at x equals to 2 micrometer, steady state electron density. So now since this was p type, we were given that p naught is 10 to the power 17 and Ni is 10 to the power 10. Now we know that what will be the electrons? Electrons will be Ni square by p naught, mass action law. Okay, from mass action law, you see it is very low, 10 to the power 3, right? Compared to p naught, it is very low because it is a p type, so p naught is high, 10 to the power 3. Okay, fine. But do I really need to find this? Let's see what they have asked. Closest approximation of the steady state electronic density, right? So what is the steady state electron density? The total density is n naught plus delta n. Okay, and this is given as n naught plus, what is it? N naught plus, there is one more thing that was given, right? Np naught. Np naught e to the power minus x by Lp. This is the expression. So this is 10 to the power 3 plus, this was 10 to the power 14 into e to the power minus x by, what is Lp? Lp is this, electron and hole diffusion length. You see, electron and hole diffusion length, right? So hole diffusion length is 1 micrometer and electron diffusion length is, sorry, this is Ln, I am talking about electrons, Ln, okay, Ln. So it is given as what? Ln is given as 2 micrometer. 2 micrometer, see I am writing the unit, it is very important. Why? So n equals to 10 to the power 3 plus 10 to the power 14 e to the power minus x by 2 micrometer, right? And at what x it has asked you to find? It has asked you to find at x equals to 2 micrometer. So at x equals to 2 micrometer, n equals to 10 to the power 3 plus 10 to the power 14 e to the power minus 2 micrometer by 2 micrometer. So the unit cancels out. Remember, if they had asked for 2 centimeters, you would be have to require to change the unit, right? Very important, especially when it is numerical answer type. You cannot cross check with the options. You have to remember how to play around with units. If you solve this, you will get 10 to the power 14 into 0.367 plus 10 to the power 3. So this is a very big number, right? That means it is approximately equal to 0.367 into 10 to the power 14, and this was your answer. Okay?
Yes.
Okay. So now I hope this was clear. Now I will tell you, there was another question, but we won't solve it. This question we will solve in after 2 weeks. Okay. Next class will be CMOS MOSFETs. Then we will take this again and we will solve it. By that time you guys can look into it. This is GATE EC 2022 question 56, based on the similar concept. And this question, you see, this is a numerical answer type question. You see there is a dash here and there was no option. This was a very lengthy question. So when I started solving it, it was a very lengthy question, first of all. So GATE EC 2022 question number 56. It is a lengthy question. It involves lot of calculations. On top of that, it is a numerical answer type. That means you don't have options. This type of question, if you solve in GATE, there is a very high chance that you will do mistake. And this is for 2 marks. And the time you will spend in doing this question and earning 2 marks, you might be able to do 6 marks in total, some other question. Maybe you will finish 3 questions in that time. You understand my point, right? Lengthy question, lot of calculation. It is having on top of it is a numerical answer type, and these kind of questions, they actually reduce your confidence level during GATE exam. What happens is, you will take it in your ego. How it is not getting solved? It should get solved. You will think like that, and then you start solving. That is not your aim in GATE exam. Your aim in GATE exam is to solve as much problems as you can and earn marks. So these kind of questions, when you come across these kind of questions in GATE exam, your first response should be, let's leave it, we will see it in the end. And how will you understand whether it should be left or not? That will come through practice. Okay, when you have practiced and you know the formulas, you will go over the question and you will remember the formula and you will think, oh, it will need time, let me not waste time on this, let me leave it, then I will come back to it later. Now one more thing is, if you see, this was question number 56, right? There are total 65 questions in GATE and this was question number 56. This was one of the questions that they had put in last. Normally in GATE paper they do these things, that very hard questions they will put at last. The reason behind it, that psychology, they don't want to disturb you. Okay, and when they have to set very tough paper, initially they will put this kind of questions. The student will look at the question, he is gone, right? So it's very important to up your game and up your mental status during the GATE exam. Always keep it up, always see what all questions are there, what is the easiest one, let me start from there. There is one more strategy that they take in GATE exam. If they want to make the paper appear more difficult, they will mix questions. Like they will put one question of network, the second question will be from EMT, third question will be from maths, fourth question will be from signals, and then one more network question. So what they have done, they have mixed it in a way where two subjects which are actually completely unrelated to each other are there, one after other. So what happens, your brain has to switch, right? Your brain will switch. You are doing a network question, again you have to switch it to maths. So from network you are jumping to, say, algebra, linear algebra or matrices. So your brain is switching, right? So some people, they have this strategy that they do one subject together, like first if they start with networks, they find all the network questions, they solve it. That is also a good strategy. If you don't want, you don't do that. And suppose in networks only, where that strategy fails, suppose in networks there is 5 questions and 3 of which them are very tough. Now that strategy failed. You started solving the question, you saw there are 5 questions, 2 you can solve, 3 you could not. So don't get depressed, leave it, go to signals. 2 questions network you have already solved, go to signals, start solving signals. So GATE is mainly more about strategy, so we will keep on discussing this with in other lectures as well. Okay, so here let's start again. So the p-type semiconductor with 0 electric field. So this question you guys can try once you have gone over this topic. We will do it in next to next class. Okay, so now let's start with Chandrasekhar's question. So Chandrasekhar, you are here, right? Okay, he's there. So he has sent me 3 problems which were actually quite simple as compared to what had been asked in 2021 and 2022. Okay, you can see this is again an illumination question. Now one more thing here is, this is a numerical answer type, right? I think it was asked in GATE, it was 2015 question, I think. It was 2015, if I am not wrong, this was set 2 question. Okay, so I did not have this question in my set, I was set 3. So this was set 2 question, EC, GATE 2015, and if you see this is a numerical answer type. That means even if you don't know this concept, suppose you did not know this concept, then also you can try it, because there is no negative marking. Agreed? So did you understand my point? This is a numerical answer type question. You don't know how to solve it, but you can guess, because it's a numerical answer type, there is no negative marking, right? Okay, now if you see, this question says an n-type silicon is uniformly illuminated and it generates 10 to the power 20 electron hole pairs. What is the unit? Per centimeter cube per second. So in 1 second, 10 to the power 20 per centimeter cube electron hole pair is generated. Now minority carrier lifetime. What is the minority carrier in n-type? Holes, right? So tau p is given as 1 microsecond or 10 to the power minus 6 seconds. Be very clear with the units. Okay. Now in steady state the whole concentration is equal to, now Chandrasekhar, you are following, right?
Yes, ma'am.
Okay. So n type, first point, n type silicon, minority will be holes, right? It has said in n type silicon it generates 10 to the power 20 electron hole pairs. Minority carrier lifetime is given, that means holes lifetime is given. That means now you see, you don't know this concept, you are a layman. What you will do? You check the unit. This is 10 to the power 20 centimeter minus 3 by second or centimeter cube by into seconds. This is its unit. Let me write it again. 10 to the power 20, this the unit is centimeter cube second. If you multiply this with tau p, seconds cancels out. What is the unit? 10 to the power 14 centimeter minus 3. That is what they have asked, right? They have asked the whole concentration. So they are saying in steady state the whole concentration in the sample is approximately 10 to the power 6, 10 to the power x. So therefore 10 to the power x equals to nothing but 10 to the power 14.
Yes,
Right?
ma'am.
Now there is one problem here that they should have mentioned. 10 to the power x, they should have mentioned the unit, na. So this is a problem from their side. Okay, but what you will do, if there is nothing mentioned, you take what is given, centimeter minus cube. Always it is in centimeter only. Okay, they should have given the centimeter minus 3. So once it is given, you just compare it and you find x equals to 14. You understand? So this was a numerical answer type worth taking a guess. So this is how you should guess in GATE exam. You should not guess out of nowhere. And I am not saying asking you to guess if this is a option based question. It might have happened that this question had some other values and it depended on that relation e to the power minus x by LP, because e to the power minus value is something that you can calculate from calculator, right? E to the power minus 1, minus 2, that you can calculate. So those kind of questions are also there where you cannot guess. But this, if you did not know, a simple guess would have done. I hope this question is clear. Okay. Now
What is the formula, basic formula for this question?
what is the basic formula for this question? Okay. So I had shown you that formula earlier when I was showing the list. So basically the whatever electron hole pairs is getting generated, if I take it as alpha, multiplied with the time will always give you the concentration at that particular time. There is a very commonsensical question, like whatever the concentration is at that particular time, after that particular time, that will be obtained if you multiply with the electron hole pairs generated. Okay. So you cannot mug up the basic formula for this, please understand. Don't mug up. You go through the lecture series and see how this was arrived at. Okay. So now the next was this one, right? Question number 39. I think this was from GATE 2016. Okay. The uniform donor density is given, ND is given, optical generation rate of the electron is given. Again the generation rate is given. You see the unit, centimeter minus 3, S minus 1. The incident radiation is turned off at T equals to 0. Assume low level injection to be valid and ignore surface events. Carrier lifetime is given as tau P0 and tau N0. Okay. Again the tau is given, your optical rate is given. Right now we saw something. It is saying whole concentration at T equals to 0 and whole concentration at T equals to 0.3 microsecond is. So at t equals to 0, we had been told, okay, so this is the kind of graph that you get. So you were asking about this thing, right? The basic formula, this is the basic formula, delta p is equals to g dash tau p, okay, and at t equals to 0, once the light is off, it starts decreasing, carrier concentration. Now this is what I had told you earlier, that the total electron will be n naught plus delta n is the excess, okay, Pn is Pn naught plus delta p, okay, n naught is delta n is given by this delta n into e to the power minus t by tau n. Why this e to the power minus t by tau n? It is this relation is e to the power minus x, right? This is e to the power minus t type of relation, right? So from here it comes, okay. So what they have asked is, whole concentration at t equals to 0, okay. So first we will see whole concentration at t equals to 0. What is tau p 0? 0.1 microsecond. What is g opt? That is the generation rate. So what will be the whole concentration at t equals to 0? What will be whole concentration at t equals to 0? 0.1 microsecond you have to change into seconds. Is this clear? Simple, right? Now this can be understood by one more way, that this thing, whole concentration we are seeing in the semiconductor. So Pn naught plus g dash tau p e to the power minus t by tau p, t is 0, so Pn will be Pn naught plus g dash tau p. Now you will say, where is this p naught? So this is almost negligible. The Pn naught will be almost negligible with respect to g dash tau p. How did I find out Pn is negligible? What is Nd? 5 into 10 to the power 16. What is Ni? Ni is not given here. You should remember Ni is 1.5 into 10 to the power 10. All in per centimeter cube. Okay. So Pn naught, when you see, it will be Ni square by Nd. And this comes out to be, I think this will come out to be around 4500 per centimeter cube. So when you compare it with what you have got here, g dash tau p, this one is a very big number. So this is approximately equal to 1.5 into 10 to the power 13, majorly equal to, right? Okay. So the formula that was used was this. So these are all excess carriers in semiconductor topic. As I had said, Pn means holes in n type, Nn means electrons in n type. So this is type and this is the carrier. This one is the carrier. Okay. Now similar thing also goes with the electrons as well. Now they have also asked you at t equals to 0.3 seconds, microseconds, right? So now what you will do? Come back to the formula. Now we know that since Pn naught is very small, Pn is approximately equal to g dash tau p e to the power minus t by tau p. Now Pn is equals to g dash, what is it? What was it given? 1.5 into 10 to the power 20, right? I think it was 20. It was 1.5 into 10 to the power 20. Tau p is now what? So this is always 0, tau p at 0. So basically I should have written it in this way, so that, okay, so at t equals to tau p naught. So basically that is tau p naught. Not write it like that. This is basically tau p naught, and that one is tau p. Okay, so am I missing something here? So this is tau p naught, this is also tau p naught. And if it is n, then it is g dash tau n naught e to the power minus t by tau n naught. Okay, so e to the power minus t by, so coming back to the formula, 1.5 into 10 to the power 20 into tau p naught is given as what? 0.1 microsecond. Tau p naught is 0.1 microsecond. Tau p naught is 0.1 microsecond, and you have to find that t equals to 0.3 microsecond. So you put tau p naught as 0.1 microseconds e to the power minus 0.1 by 0.3. See, here you need not put into 10 to the power minus 6. I think the slide is a bit slow. So Pn is approximately equal to 1.5 into 10 to the power 20 into 0.1 into 10 to the power minus 6. This is the time, 0.1 microseconds. This was that concentration generation rate. Now in here, if you see, it is e to the power minus t by tau p naught. So t is also given in microsecond, tau p is also given in microsecond. So need not write it like this. This is waste of time. You understand? Writing it into 10 to the power minus 6 and all those things. You know both are in microsecond, they will anyways cancel out. So if you now solve this, you will get, I think the first is the option, so 7.47 into 10 to the power 11. Is this question clear, or should I repeat it? So we start with this. So this is excess carriers in semiconductor. Go over this topic well in NPTEL or any other source. If you have, you go over this. And these are the main two governing equations that we saw, right? G is the generation rate. Now then you will see that as you solve in the question, carrier lifetimes are given. Everything that is needed in the formula is given. T equals to 0, t equals to 0.3 microseconds they have asked. Okay, and this was an option based question, so it could have been easily solved. So this was the second question that Chandrasekhar had asked me. I am moving over to the third question, which was a 2010 question, and it is a very simple question. Okay, basically voltage, what they have given is, they have shown you the voltage that they have applied to a semiconductor, and they have shown that okay, ND value is 10 to the power 16 in this semiconductor. Okay, ND value is 10 to the power 16 in this semiconductor, and your mobility, electron mobility is 1350. So now you have to find out the drift current density, and you have to find out the magnitude of electric field. So at equilibrium, your electric field is given by V by X. Okay, so whatever is the specimen, whatever is the voltage that I have applied. So basically this is 1 micrometer and this is 1 volt. Okay, so this was basically that it is a thermal equilibrium. Okay, so as if your distance also varies, then the voltage that is being experienced at that point will also be different, right? So therefore when you are taking the electric field at thermal equilibrium, it is constant because there is no flow of charge carriers through it. It is constant there. Therefore when you are finding it, you are not finding it with 0.5 micrometer. Okay, so basically electric field is, so in the question I think Chandrasekhar's doubt was that they have asked to find it at x equals to 0.5 micrometer, but when they are calculating electric field, they are taking x equals to 1 micrometer. So this was actually at thermal equilibrium. Okay, the entire semiconductor is at thermal equilibrium, and therefore the electric field will be given by what is being applied to the total is what you will get. There is no variation. So this will be 1 volt by 1 micrometer. So it will be 10 kilovolt per centimeter. That is what it will come, and that is what it is given in the equation in the options. And in question 53, that is basically directly using the formula. You can just put it and get the answer. Okay, Chandrasekhar, is that fine? So you need not take so as I mentioned, it is at thermal equilibrium, there is no motion or nothing is happening there. That is why they have particularly mentioned that it is in thermal equilibrium. Okay, so that is why you have to be very careful about this terminology. So I remember this question when I was also practicing, I was doing this mistake. Okay, but you will see, Chandrasekhar, that none of your answers will match if you take x equals to 0.5 micron. That is also one thing, you can think it of like that. Okay. Okay, so I think I am way over time. So we will start with we'll do small signal MOSFETs in our next class. By that time, 2 weeks you guys are having. You do it, do the subject of EDC if you can, and we'll again go over these topics next week. We will again go over these topics. Yes, Chandrasekhar. You can unmute yourself and directly tell me instead of typing.
Can you suggest for analog electronics?
What you want?
Lectures or notes type?
So for
basic.
See, analog electronics, a lot of things are available. Okay, so as I said, for practice you can use Schramm series. The back exercise of Cedra and Smith is very good. Okay, now for lectures, NPTEL, I haven't checked NPTEL. There was one IIT Madras professor who has given. You check with IIT Madras, okay? Check for analog electronics. Don't check for IC design. There will be many for IC design. Analog IC design is different. That is more in depth with the designing part. So this is not what you should look. Your gate syllabus is this. So analog electronics, IIT Madras, they will be very old lectures. Okay, the professor is old. So I had like, you know, right, in NPTEL they will teach in board, blackboard. So it is that lecture where he teaches in blackboard. So one is this, and if you want to go with something different, you can check Razavi's lecture. So Razavi has this 2 set of lectures. One is for IC design, one is for analog electronics. So I think the first part 1 is analog electronics and part 2 is IC design, and in part 1 there is a series of lectures. Okay, a lot of lectures, and then in part 2 a lot of lectures. Okay, so this is what I will suggest for analog electronics. Okay, and your electric field, this question of electric field, if you want to understand more in detail, then maybe in next class I will come up with some kind of model where we will see how the behavior of electric field with semiconductors is. Okay, but we will take semiconductors again after next class.
And you are taking analog electronics also, na?
EDC and analog. So next analog electronics I will go with small signal analysis of MOSFETs. Okay. And we will go with, actually in Razavi's analog IC design book, chapter 3 is amplifiers. I am not asking you to do it, but we will go with some problems from back exercises here, because I think next is what this is going to be coming in GATE. I think so, because
Ma'am, please also take lecture on digital electronics.
Sorry?
digital electronics.
Again in digital electronics also you will find IIT Madras professor is there, okay, and his teaching
That is
also is I think on board or something. So I actually try to watch all these old NPTEL lectures especially because they are very good, and the new ones are actually mostly related to the industrial type of things, the advanced ones. So always go with the keyword of the subject, like digital circuits. So digital circuits will be obviously towards the basic thing, okay. And also you can search in YouTube as well for digital. In YouTube I think a lot of lectures are there for KMAP,
ma'am,
state
because that
machines and
takes a
everything.
lot of time because
You
lot
will
of
have to
time is
invest,
needed.
you will have to invest time. So if you are targeting 2023, then your concept should have already been built up, and then you should be at a point, as I mentioned right in the beginning of this lecture, that if you are targeting 2023, that means that you are already at a point where you know the concepts and you are only going to practice the previous year. Or if
Ma'am, for analog electronics, you are talking about K. Radhakrishnan Rao.
I think so, yes.
And because his lecture on analog signal processing first.
It is analog signal processing, that is what I think he has mentioned.
Oh, yes,
Just
yes,
tell
yes.
me the name.
K. Radhakrishnan Rao.
I'll just
Radhakrishna Rao.
I'll just
IIT Madras.
cross check it, okay.
Okay.
Cross check it, just wait. No, these are basically newer, but it is written analog circuits and systems. Okay, so what you do is you Google, instead of checking it in NPTEL, you Google it. So when you Google it, you will find, I'll share my screen and show you. So you are able to see, right? See, I just googled Radhakrishna Rao IIT Madras, and I don't know, I think he is the same person. I saw these lectures, these are very old, okay, and I think it is the same person.
Yes, ma'am.
This is the same person, Radhakrishna Rao, okay. So you can go over this.
And this series is called that analog signal processing.
Okay, so okay, would have changed the names or whatever. So this is analog circuits and systems as it seems here, and maybe this one is analog signal processing, I don't remember it. Okay, so you can go over this lectures as well. These are very good lectures, like this will come handy afterwards also, like after clearing gate also, when you have to go towards these interviews and everything, these come very handy. Okay, so is there anything you want to change in the lecture, any feedback?
Hello, ma'am. Ma'am, everything was fine, but little more explanation. Like you have sold all the formulas for that analog electronic devices, and but for digital circuits also, can you just
I actually
explain
am
this?
only taking EDC and analog. So digital circuits, I think there are others who are taking. So they will be handling that. So for them you
Okay.
can take. So and I understand that these formulas might be very fast for you, but I think once you go over the topic and come back and see the lecture again, you will be able to understand more. Or you don't have to see the lecture also. I mean, you can see the questions and you will be able to understand.
Yes, ma'am. I have all the books also, and for
Yeah, you just start preparing. So I think it can be done. So I have put my Google site in the chat box. Okay, I will be putting a different section of gate and I will put the notes in that. Okay.
Okay, ma'am.
Okay then, guys. Bye. So it will be next week same time. Okay, and we'll take MOSFETs.